So in the previous class, we discussed about the binomial probability law, which will have a specific probability distribution whose probability mass function is given in a certain way. Okay, and we know the parameters are small n and small p. That we know. These are the parameters. This is a probability distribution which a particular system can follow. Like binomial distribution, there is one another discrete probability distribution that I'm going to define right now. Okay, I will send the topics to the WhatsApp group. You will get to know. So another probability distribution is if capital X be the discrete random variable, if capital X be the discrete random variable, carefully listen to me. This is very important. If capital X be the discrete random variable whose probability mass function is given by the formula probability of x equal to small x, which is equal to e to the power minus lambda to the power x by x factorial. X is equal to 0, 1, 2, and it goes on. I'm not explaining Poisson distribution right now. I'm not giving you the motivation for studying Poisson distribution, but I'm going to relate. I'm going to say you something which is very important. Just keep in mind. So probability of x equal to small x is this. Okay, this is the way by which the probability law is being defined. If it is so, and for completeness, if I write 0 otherwise, because all the outcomes are mutually exclusive, if one happens, the other will not happen. If it is so, then the random variable capital X is said to follow Poisson distribution. And in this probability law, there are also parameters present. What are the parameters in this particular distribution? You see, small x is the number of outcomes, the type of outcomes that may appear. X are the, whenever we talk about x, it is actually we are talking about the number of successes that we are interested in. So it is not a parameter, because in binomial probability law, x was there. X was not the parameter, remember. It is the value, it defines the values. E is not a parameter, because E is an exponential. It is the exponential function. E is actually the e to the power x. It's a kind of function that we are operating on the values. What is the parameter then? Over here, the parameter is lambda. Lambda is the parameter. So if you know the lambda, then you know the Poisson probability law. So here in this particular case, the parameter of the variable x, parameter of Poisson variate is equal to is actually lambda. But what is lambda? What is lambda actually? Lambda is defined in the following manner. Lambda is actually number of experiment n multiplied by the probability of success. That is your lambda. So to put it in other words, we can write probability of x equal to small x in the following manner also. It is e to the power minus np to the power x by x factorial. Okay, and you know the definitions of x, n, and p. Okay, these are the number of experiments and probability of success as defined in the binomial case. So now, as the definition of this is clear, then before I end my today's class, just give me a minute. I'm going to say something to you very interesting. That We already know that probability of x equal x and probability of x, this chart that I'm considering for the coin tossing problem, x was having the value 0, 1, 2, 3, 4, and the probability is already, I have already marked up the thing. So it was 4 by 6, 1 by 16, 4 by 16, 6 by 16, 4 by 16, and 1 by 16. মুখস্থ হয়ে গেছে. So these were the probability distribution, and if now you know that corresponding to the binomial probability law, if someone asks you what is the probability of one success, okay, then automatically instantly will reply that it is 4c1 p to the power 1. P is half, you know, I discussed in the previous class, and q to the power 4 minus 1, that is 3, and that is equal to 4 into half to the power 4, which is 4 by 16. Is quite obvious because it is given already here, and 4 by 16 means 0.25. Okay, so this is the probability. So by binomial probability law, we can calculate the probability. Now, if someone says, is your distribution of coin tossing follow the Poisson distribution, Poisson law, can you calculate the probability? You will say, yeah, probably yes, because we know the number of experiment and we know the probability of success. Why not Poisson? Why binomial always? This can also be done by Poisson. So okay, fine, let's do it. So we have n is equal to 4 and probability of success is half. So by Poisson law, np is equal to, now according to the parameter, np is equal to 2. Okay, so everything is known, so why not Poisson? So someone thinks that, okay, let us not apply the binomial probability law, let us apply the Poisson probability. So if he does so, I'm using this result right now. He'll be writing e to the power minus 2 and 2 to the power x by x factorial. This is his probability formula. And if he now wants to get probability of only one success, so he will instantly write that it is nothing but e to the power minus 2, 2 to the power 1 by 1 factorial, and thus he will be getting the value. Let me calculate. He will be getting the value e to the power minus 2, this, yeah, he is getting the value 0.27. So two different probabilities are coming. Okay, so at this point, the student may, some people may say that, okay, 0.25 and 0.27, there is no much difference in this. 0.25 means out of 125 times it's happening, one success is coming, and 0.27 means out of 127 times it's happening. So okay, extra 2 times it is happening. So what's the what is the point? We can do this particular problem by Poisson law because we know the parameters. But the question is, can I really do so? Can we neglect these probabilities? Is it negligible? This is a very important question. Have I done anything wrong to the system of coin tossing? Okay, how can a particular problem be justified by using two probability distributions, two different types of probability distributions? Okay, so there lies the question. There lies the question, and my brief answer to the given, my brief answer to the question posed by me is that whenever in this particular problem we applied binomial probability law, that was okay, no problem with that. But if you want to apply the Poisson probability law to the given system, it is wrong. We cannot apply Poisson law to the given system for some reason. For some reason that I have not discussed in this particular class. Okay, what is the reason of doing this? Why am I not be able, I'm not, I mean, it is not authentic to apply Poisson law to the coin tossing problem. That will be discussed in the next class. Okay, so technically, mathematically, we can really apply Poisson law to the given system. But identification of the system and its corresponding probability law is actually very important. I have the tool, so I am applying it anywhere. It is not, I mean, required. It is not recommended. So with this, I'm going to conclude my today's session. Hope you are able to understand whatever I wanted to talk about. If you have any doubts, because I have time, I do not have any more classes. Probably you have class. So if you want to ask me anything, you can ask, or you can leave the classroom. Okay.